So I welcome you all participants for this last day of ACT Atal sponsored FTP on AI ML based reconfigurable antenna design for next generation wireless communication. Thank you all. This is the sixth day and we are going to have the last sessions today. Thank you all for your active participation. So today's first speaker is Dr. Zaid Muzahir Abbas. He received his PhD degree in electronics engineering at Macquarie University, Australia. He has been a transmission engineer for Alcatel Lucid Pakistan, RF engineer with Comscope Australia, senior antenna designer and senior principal engineer with Benelux Technologies Australia. He has lectured various courses at Comsats University, Pakistan, and in Australia with Western Sydney University, Australian Catholic University, and University of Sydney. Currently, he is working as a lead antenna design engineer with GME Australia. He has been a visiting researcher at Electroscience Laboratory, Ohio State University, USA, Queen Mary University of London, UK. He has also received several prestigious awards and fellowships, including 2020 IEEE 5G World Forum Best Paper Award, 2019 IEEE NSW Outstanding Young Professional Award, 2018 Young Scientist Award from the International Union of Radio Science, 2013 IRO Postgraduate Fellowship, 2012 IMQRES Award for PhD, and Research Productivity Awards in 2012 and 2010 from CIIT Pakistan. He is co-inventor on about 20 patent applications and co-author on more than 200 research publications. His research interests include wireless mobility solutions, base station antennas, 5G antennas, millimeter wave antennas, 3D printed technology, metamaterials and metasurfaces, high impedance surfaces, frequency selective surfaces, electromagnetic bandgap structures, artificial magnetic conductor, beam steering, UWB, multiband antennas, flexible antennas, CNT yarns, CNT graphene based antennas, reconfigurable antennas, RFID, sensors, and development of antennas for UWB, VHF, UHF, and W band application. We welcome you, sir, and he was a chairperson for various conferences, Region 10 coordinator for IEEE MT, MWTS in professionals. We welcome you, sir. Thank you for accepting our invitation.
Thank you.
Thank
Thanks
you.
for the nice introduction. Let's start without any delays. You can see my screen, and I believe you can see my presentation.
Yes,
If
yes,
anyone is having their microphones on, please put them on mute, so it will be easier for everyone to listen without any disturbance. Can you just confirm you can see my screen?
yes, we can.
Okay, great. There is some banging sound from someone in the one of the audience. So if you can mute that person. Okay, great. Now it's pretty quiet and good. Okay. Um, uh, Shine has already introduced myself, so I will not be going into too much introduction. I'm pretty much affiliated with IEEE over the time, and currently two important things are I'm the chair for New South Wales section and Region 10 coordinator for NTT Young Professionals and EMC Young Professional Ambassadors for um, various activities through EMC Society. I work in industry, work in academic sector over the time, so I will try to blend both sides for you guys. So the title of the talk for today is Wearable Antenna Solutions for Body-Centric Wireless Communication Systems. And these are the areas where I work from wearable to flexible, multi-band antennas, high-gain antennas, and 3D printed antennas, and different kind of RFID sensors, metasurface based things for different applications. Okay, let's straight away go into the wearable technology. So I will introduce you to the wearable technology, then we will look into the key aspects of body-centric communication, and then we will go further from there into different developments that have been done over the time. So, what is body centric communication? It is a communication either from human to human or on different access points on the body of a human. So it combines wireless body area networks, it could be among the sensors, or you can form a wireless personal area network. Peter S. Hall and Young Hao, they have done very significant work over the past decades into this area, and they have done a lot of work, and there are a couple of books that are available online that you can go through from both of the prestigious researchers. Okay, so if we divide it into further, you can have three different kind of communications. When the communication is from one person to another person, that will be referred as body to body communication. Then there could be a communication from the body of a person to any access point, let's say a wireless access point in a building, it could be a base station, or could be any point. So this is referred as off body communication. So on body is another one. When different nodes on the body communicates among themselves, this is on body communication. Then there could be an implant inside the body, and if the implant is communicating to a sensor outside the body, that will be in body communication. So in body, on body, and off body communication, and there could be body to body communication. So I believe that gives a scenario to all of you. What are the different kinds of communication we are looking in? And again, these communications are pretty much dependent upon the environment, because human body is lossy, and how you handle the communication in a lossy environment. Again, the range, the penetration of the signal, and the battery power, these things are also important. Okay, use cases. I have put one scenario in front of you. There could be a person, and there could be multiple sensors on the body. They need to communicate with each other. There could be a communication from one person to another person in an arrangement. It could be communicating from here to an access point. This is one of the scenarios. We can think about another scenario where, um, let's say it's a soccer field. Some players are playing a soccer match. They need to coordinate among each other. They need to be monitored for their body temperature. It could be the movement of their muscles. So multiple things could be there. It could be a scenario where firefighters are handling a fire in a particular area, and they need to communicate between themselves and also to the fire truck that is nearby. So that kind of communication could be there. Okay, there are multiple other applications. Firefighting, there could be military applications, there could be health monitoring, there could be application sports, and into very smart kind of applications, to have some kind of restricted or concealed arrangement of the sensors. Here you can see that the sensors can be in earrings, they can be embedded into the socks for sports people. It could be communication. I believe most of you might be using it in your daily life now in terms of smartwatches, and to communicate among yourself through the smartwatch. Okay, can someone just unmute and let me know that you can hear me, because on my screen I can only see the presentation. If I'm offline,
Yes, sir.
most probably it will not be letting me know.
Yes, sir. Yeah.
Okay, that's good. That's good. Thank you. Okay, now the question is, if we are talking about the wearable technology, where to place it? There was a survey back in time, where there was a question asked to a set of people, um, to identify what could be the ideal location of a wearable device. So it could be into different body parts. It could be on the wrist, it could be on the arm, it could be on the legs, it could be in the footwear, it could be on your chest, on your shoulder, on your head. It could be embedded in the glasses like Google Glass. So there are multiple possibilities, and all all the locations, they have their own pros and cons. Okay. Now it depends upon where you are putting the antenna, and definitely it becomes a key challenge because our body is made up of a lot of water content. Then you have the skin, then you have the fat, and then the muscles and the bones. And the thickness of fat, skin, and muscle and the bones is different at different locations over the human body. When you have more water content, it becomes more lossy. Okay, let's talk about different requirements and challenges. So you can have different frequency bands. You can use for medical implants 400 megahertz, 402 to 405 megahertz. You can use ISM band at 433 megahertz, 900 megahertz. Normally we use 915 in 902 to 928 range. Then you can have a Wi-Fi range 2400 to 25, and then the extended range from 5.7 to 5.8. You can also use ultra wideband communication from 3.1 to 10.6 gigahertz. You can also use GSM and personal communication services 1800, 1900. You can also use the WLAN applications, high frequencies such as 60 gigahertz. If you're talking about 5G, then you can use the commercial bands from 690 to 960, 1.7 to 2.7. And then 5G third band varies from geographical location, starting from 3.2 all the way to 4.2, or zero point 0.3 gigahertz of band is normally used. Okay, when you put sensors or transmitters and receivers on different parts of the body, then radiation pattern is important because we don't want the radiation goes towards the body and it gets absorbed. Okay, so from one point in the body to another point, you can communicate. This is on body. If you're talking to a device that is away from the body, off body communication, and you can also talk to implant in the body. So radiation pattern, it could be like this, or it could be just focused on one side. If it's focused on one side, this means you can focus the energy into a particular direction, and then it becomes an off body mode. When you are communicating over the body, you need more signals over the body. So these are two types of radiation patterns that we will be focusing on. Okay, so um, when you put the antenna towards the body and it doesn't have a ground plane means that there is a full metallic structure at one end of the antenna. It's a PCB with a dielectric. On the top you have the radiator. On one side you have a ground plane. If you have a partial ground plane, it has a different pattern. If it's a full ground plane, you can consider that it acts like a mirror. So the energy that is going up and down sides, both sides, if you put a mirror on one side, it will reflect all towards the upper hemisphere. So that will be the role of the ground plane in terms of radiation. So this helps in reducing the radiation that goes towards the body. So a full ground plane is a good solution, and then once you have less radiation towards the body, you will end up with low values of SAR, and the impact of the human body can be mitigated, or it could be significantly less. So there are conflicting requirements in terms of bandwidth, impedance, radiation efficiency, and the placement, and you have to keep it low profile as well. So the height of the antenna should be low. So we came up back in time where full ground plane can be used, and I will be going through some of the antenna designs with full ground plane. Then I will be talking about planar antennas into various applications, and then I will be going towards the UWB antennas and then analysis over the body. So I think I still have good amount of time, so let's go. Okay, so we started with one of the design requirements for some antennas that could be fit into the wristwatches or something similar. So we defined our band, what bands, 2.45 gigahertz, 5 to 6 gigahertz. These are the two targeted bands. We need the radiation in such a way that it covers on-body application. This means we need to have a wide coverage area to cover more area over the body. So the off-body communication is not the goal over here. We want to have a full ground plane. It will minimize the radiation that goes towards the body, and it will also help us when the antenna keeps on changing the distance between the body and itself. Um, and we also want it to be less sensitive to as it changes the gap between the body and the antenna. Other options, other requirements are lightweight, low cost, and compact. So we started with one antenna where we have a feed over here, and we did coupling to feed the arms. These arms are quarter wavelength, very basic kind of structure, but the good thing is that we adjusted the gap in such a way that the coupling was right. We put it on the body, and then the distance between the antenna and the body was varied. You can see it has a wide coverage area. This point where you see a dip, that is the feed point over here, and if you put the radiation, it goes all the way around over here. So if you put on the body, it will have a wide coverage area. That's what was required. So the width is 14 mm and length is 80 mm. And when you put it on your wrist, you can easily get it into the strap of um, the watch. Later down in upcoming slides, I will show in comparison to one of the wrist watches. Okay. Then we came up with some analysis. If we change the gap that is over here, what will be the impact? To understand the performance, we optimize the gap, and then we change the distance between the antenna and the body, and you can see that the variations are very minimal. So the intended band is over here, so it always stay within the band even though the distance between the antenna and the human body is changing. Okay. So then we came up with the dual band. We modified our initial design in such a way that we can add an additional band. Previously, it was just 2.45 gigahertz, and then it becomes an other band as an included version, where 4.9 gigahertz, that is a WLAN band, plus it is also for public safety, widely used around the world. So you can see that there is a high level of stability. Even if we change the distance, both bands are pretty much stable, and you can see that again a wide radiation um, area is there to cover most of the area over the body. Okay, then we improve the performance further by adding some stubs that help us to have a better radiation pattern and to fill the one of the nulls that was available in the previous designs. And then we put it into a condition where we use the substrate that was Arlon isoclad 933. It is a semi-rigid kind of thing, and if you bend it, it can easily be bent. So we put it onto the arm. You can see that there is a skin, fat, and muscle layer, and there is a bone. So those values are available from very well-known database, and you can see that we did a little bit of offset of the bone. So if you look at your arm and try to judge the bone, on one side you will see the muscle is less, and on the other side it will be more muscle. So we did the analysis of this kind of antenna, and it was performing pretty good. Here you can see it's just a normal wristwatch. I put it against one of my watches, and you can see it's pretty small size, so it can easily fit over here. So you don't have to go for too much bending, and it can easily be fit into that one. The connector, depending upon how you put it into the device, the connector doesn't need to be there. You can replace it with a cable or something else. So it was having a pretty good stable performance when you see it against different varying distance between the antenna and the body. So we put it onto a different curvature to check the bending. So these are some of the bending analysis results, and then this is the proposed antenna measured results. Okay, a little bit more better view of the analysis. Here you can see that these antennas, they have pretty much wide coverage area. So if we look at that one, it looks like a balloon. On the upper hemisphere, these are the two cuts on the vertical side, the center and the rightmost figure. And this one, when you see from the top, you can see it is having pretty much omnidirectional. When we started, this area was having a null. If I just go back and let you see the same thing, this was the null, and we were able to fill up this null significantly over here, and you can see that it is pretty much kind of wide omnidirectional pattern. So this was a pretty good achievement back in time. And then we put it onto different body models. So we made body phantom with some kind of mixing of ingredients. So they can be found over here: gelatin, glycerol, and some other things. So we added some salt to increase the conductivity, vegetable oil, soap, and some of the colors to differentiate between different layers. So these are the Maillard values of the phantom and the targeted values. This work was done back uh, when I was at Ohio State University. Um, that was a thin plastic body outline, and we filled it with the mixture of those things. And um, on the top, we put additional two layers with the same thickness to represent fat and the skin, and this is equivalent to the muscle inside the body. We did the communication analysis between different antennas from different locations to see that the communication is good enough or no. And we checked it on the shoulders, abdomen, on the chest, and different places. We also did the Wi-Fi testing for this one by integrating it with the Wi-Fi modem, and that was showing a pretty good results. When you remove the antennas, you can see the signals are gone. So this means it was working. And looking at the size of the antennas, I have shown that it is pretty much in comparison to a wristwatch small. So you can easily integrate into a Fitbit or any other kind of wrist or wearable devices. Okay. Now from there, we have already spoken about single band antennas, dual band antennas, and then antennas with a controlled pattern with wide radiation coverage. I will talk about some of the reconfigurable antennas. Most of the work that I will be presenting, either I'm one of the co-authors or it is from the same group I worked over the time. Musa is one of our PhD students about to finish soon. So here you can see a simple design where it is having a ground on the side, and then you have a radiator over here. So we increase the number of radiating edges. It is on a Rogers material. It covers a wide bandwidth, and the footprint of the antenna is 30 by 25 mm. Thickness is 0.025 mm. It covers three bands: 2.3 to 2.5, 2.7 to 3.8, and 3.5 to 4.2. Okay, it can be used for WLAN and ISM applications. It is flexible because this Rogers material, it is semi-rigid. If you bend it, you can bend it, and it can be in it can be utilized into any of the applications with a bending requirement. But if you're using FR4, that is another kind of substrate like a PCB hard material, if you try to bend it, it will break. If you're looking for the reference, I included the reference on each of the slide where new work has been discussed, so you can easily go back and have a look on this one. So in this work, we started with a simple design with a patch over here, and we rotated by 90 degree and with the CPW feed, and then you can see that we started modifying it, and we can see that dual band starts coming in. Then we put the diodes, and with the diodes, it can be in a different states, either on state or off state, and you can see that either it's a wide band or it could be transformed into a dual band. The red one is a dual band. Dual band means any portion of the curve that is below -10. So this is the lowest frequency, this is the highest frequency, and the mid frequency, and it can easily be done. I will just switch on my pointer. Okay, pointer options, and here we go. That will be easier a little bit. Okay, so we did the bending into two different sides. Let's say this is my antenna, like a mobile phone. So I'm just replacing it with my hand. It can be bent like this, or it can be bent into a different side. So vertical, horizontal bending. So you can see that if you bend in either of the directions, horizontal, vertical, or you just keep it as it is, simple, then the performance is pretty much stable within the band. This is again on the other state, on and off. Then we came up with another antenna. Here you can see that instead of CPW feed was when the ground plane is on the same surface where the radiator is. So in this case, it is on the other side. So we have a full ground plane. This means the radiation towards the body should be less. And then the radiator is over here. You have the feed line. This becomes a large radiator focusing on the low frequency, and then the high frequency components are coming from here. So one is corresponding to either of these two bands, and then the coupling between the large and the small radiators that will be generating another band. So this could be the middle one. Okay. The footprint of this is 38 by 32 mm, and the thickness is 3 mm, and we get the low SAR value. So these three bands can be utilized for WLAN, different Wi-Fi applications, Wi-Fi 6, 7, 8, and it can also meet different IEEE standards. Okay, here you can see that we highlighted over here what are the bands, and you can easily see that we have some margin on the side. So still, the performance could be pretty good. We did the bending. In most of the cases, we try to do a bending along two directions. So one is the horizontal one, where my left side picture reflects that thing, and the other one is like this. It is a vertical bending. And you can see that the performance is pretty much stable. It is deviating, but not significantly. But over here, you can see that some of the bands are pretty much moving, but depends upon where you're communicating and what is your targeted frequency. Okay, then we try to do a SAR analysis. There are two standards, either it's FCC or IEC standard. We evaluate it against two different criteria. One criteria is you take 1 gram of tissue and look for the absorption of the radiation against 1 gram of tissue, and the other one is 10 gram of tissue. For 1 gram, it is 1.6 watt per kg, and for 10 grams, it's 2 watt per kg. So we evaluated that one, and you can see at different frequencies, it is pretty much below the criteria. So 1.6 and 2 watt per kg for 1 gram and 10 gram. You can see the hotspots where they are located. Then another flexible antenna that is also compact, low profile, and with a simple geometry and bandwidth enhancement technique has been used. You can see that we don't have a full ground plane. Instead of that one, we have CPW feed. The dimensions are 20 cross 15, and the thickness is 0.025 mm. It gives a wide bandwidth covering specifically 4.9 gigahertz band and WLAN band. So it is from 3.9 to 7.8. So it can cover multiple applications in Wi-Fi, WLAN, and C-band. You can see that a wide band is achieved. Then the bending analysis again into vertical and the horizontal side, and it reflects that the performance is still acceptable. Then another CPW feed antenna, again on Rogers material, that is semi-rigid kind of thing. If you bend it, it allows you to bend without breaking. Unless you fold it, then it will break. Okay, so the footprint is 32 cross 20 mm, and the thickness is again very small, 0.78. It provides a tri-band thing. So you have a CPW feed over here, some of the matching stub over here, and then you have a large radiating edge over here and another one, and the combination again gives you the center band. We have got on average more than 4 dBi gain, 4.25, 5, and 5.5 into 3 different bands. We also try to give stepwise antenna design evolution in most of our papers. We started from here, then we extended by adding more and then more, and then you can see that different design steps have the performance compared against each other. Okay, here are some my results. So they are pretty much closely matching. Another antenna with little bit of different style. So it's a monopole radiator. Some of the meandering has been done, and CPW feed also gives you 2 different bands over here. The antenna efficiency is pretty good, about 90%, and then you can see that the footprint is 15 cross 30 and thickness is 1.6 mm. This is on FR4 because sometimes the antenna is pretty small, and there is no room for the bending, so we didn't go into the bending analysis of these things. So step evolution, how the design has evolved over the time. So you started with a simple rectangular patch, then you started adding more edges to lengthen the track of the current, and then you did the loading on the top. Radiation efficiency graph showing pretty much above like 82%, and the gain is above like the unity gain. Radiation patterns, I will be not discussing some of the results in detail. So most of the time what we do is we put a comparison to compare the work against existing antennas on the same frequencies, and what are the different design and performance parameters. So in comparison, it is pretty good when you evaluate a trade-off between the size and the performance. Okay, just remind me when we have like 15 minutes remaining so I can just adjust my pace to conclude accordingly.
Okay, okay, Professor.
Sure. Now, let me remind you, we have discussed single band antennas, dual band antennas, then we have discussed antennas that are on a semi-rigid kind of materials, and they can be bendable. So we have looked into different antenna performance, design evolution, and we also have seen how they can be put near to the body. So what will be the performance? Okay. Now let's talk about UWB antennas for body-centric communication. um, UWB technology, it's a fairly wide band starting from 3.1 to 10.6 gigahertz. It provides you high data rate, low power levels. They are robust against the multipath. Most of the time, you can do a near field communication. So on a very high data rate, most of the mobile phones, they have like a very high data rate for transferring pictures. Most of you have used it. Okay. So for this particular work where we are looking at a fairly wide band, it is not easily possible with um, normal radiators that we have shown just before. And when you put a full ground plane, that becomes a little bit more challenging. If you put a partial ground plane, you can have it because it will have a signals going into all directions. But when you put it close to the body, half of the energy is going into the body. So they are not good solutions for that kind of application. So we have the challenges on the printed antennas, and most of the printed antennas with the partial ground plane, they have um, radiation going towards the body due to omnidirectional pattern. I will show one of the slides on one of our UWB antenna applications with some of the band rejection characteristics. Just a slide I have added. Okay, so ultra wideband antennas where bandwidth needs to be more than 25%. That's the criteria. So we started with a normal antenna. Um, that is monopole style. Then we added a big slot over here and chamfered the edges and adjusted this slit over here to achieve the wideband performance. So we made that one onto two different substrates. One is from Rogers, that is a hard one. Then the PDMS is a polymer based flexible rubber kind of material. The properties are a little bit close to each other, except the losses for the PDMS and the Rogers materials, they are different. Rogers is low loss and PDMS is a little bit more lossy as compared to the Rogers material. So we started with this design and then we converted this design into onto a flexible substrate, that is PDMS, and we also used the embroidery technique. So we started with the CAD model, we did digitize it, and then we did the embroidery. This work is pretty good at that time, but now the level of or the accuracy or the cleanness of um, the embroidery has improved a lot. So you can find a very fine quality embroidery, and also you can use, instead of embroidery, flexible plus conductive fabrics. So I will show you in one of the works. I hope so I have included it. So we did that thing, and you can see that as compared to the rigid to the flexible, how the results are there, they're pretty much close to each other. And on journal scale, I will conclude that they offer wideband, ultra wideband response. The gain is pretty much stable and similar on the higher end. Due to the higher losses, you can see that the gain is dropped in terms of embroidered antennas, but that problem has been overcome due to the improvement in the embroidery techniques. Okay, here you can see some results in comparison with each other. You can see that they fairly match results um, in terms of results for the rigid and the flexible counterparts. Okay. Then we did the analysis of the bending onto different radius as one of the standard things for the flexible antennas. So you can see that the performance is pretty much same as we bend it into a vertical and horizontal direction. Okay, so you can see that depending on different radius, the performance is pretty much stable in terms of starting and end point and also in terms of the bandwidth. This was done by one of my colleagues in the lab, um, Dr. Shahzad Iqbal and Yuhi. They came up with dielectric slabs that reflects the dielectric resonator antennas. They were pretty small in size. The only issue was for the more variable applications. If you have a constraint on the height of the antenna, then these are not good solutions. Otherwise, they offer a very clean wideband response. The gain is pretty high, and you can see the radiations are split. Okay, and we did some UWB FCC analysis on that one in different scenarios, and the excitation pulse performance has been compared, and there was a very significant improvement in the performance and the profile of the antenna. Okay, so this is just to give you an idea that other than the planar antennas, there could be other antennas such as dielectric resonator antennas. They also have a good performance, and they have a full ground plane, so they can be utilized for body centric or wearable applications. Kindly, if you can mute yourself if someone is having their mics on.
Yes, sir. Yes, sir.
Okay. Then we came up with another design where we have a full ground plane, probe feed in the center. These are the transmission lines. Um, we have a big radiator over here that is a little bit of squeezed into the space. So this will give you a low band. Then we have achieved a high band over here due to this small radiator. Then did we added another piece of metal for radiating through the coupling to get the middle of the band. So we did the analysis on the flat body phantom and also on the curved one, and the performance was pretty good in free space. And on rectangular and cylindrical phantom, you can see that we can have a fairly a wide band performance. We checked for the current. You can easily see that the lower frequencies are resonating at the the largest radiator. The smallest radiator is corresponding to the high frequency, and the middle frequencies are in that electromagnetically coupled radiator over here. 579 gigahertz range. You can see the radiation patterns for the off-body analysis. Gain and efficiency, you can see that pretty much stable gain. Efficiency is more than 80%. We did the SAR analysis again on the two standards, 1 gram and 2 gram, and we have followed IEEE C95 standard and FCC standards. We did some pulse analysis to check the suitability of the ultra wideband um, scenario, and again the fidelity factor has been investigated and it was pretty good. That same UWB antennas extend work was extended by one of my colleague, Dr. Shahzad Iqbal. Um, Instead of a simple feed, they modified the feed, and then they got like a really a wideband solution, and the size is reduced significantly in terms of the footprint and also in terms of the profile, and the bandwidth was pretty good. So full ground plane has been utilized, 75% frictional bandwidth. This is another work I showed you in the start for the embroidery, but what we did is we tried to mitigate incoming signals from other communication. So we incorporated in the antenna a filter. So that was one of the good works back in time in transactions. Um, we included that one, and what we did is we came up with the mathematical formula. Instead of hit and trial, you choose a frequency you want to reject, evaluate the mathematical model. It will give you a design parameter, adjust the stub values over here for that one, the length of this line over here, and it will tell you where exactly you can reject the frequencies. Here are the two examples for different bands. Public safety and wireless band we need to reject, and also 3.5 to 3.8, the 5G one, that can be rejected over here. So it gives you fairly wide bandwidth, fractional bandwidth of 120%, and ability to straight away calculate um, the design parameters corresponding to the frequency. Okay, then we another colleague made antennas with a short horn with significant 140% fractional bandwidth. We also employed antennas that radiate up and down into two hemisphere, incorporated frequency selective surfaces with 120% bandwidth. You can see that it's radiating on the upper and lower hemisphere. So one of that is rejected by putting the FSS underneath. So you can see that this is gone, and you have like doubled the energy on one of the sides, and that is clearly visible. Okay, we did some work on the polymer based antennas where we incorporated flexible copper tape on the PDMS structure, and it was able to provide a wideband behavior for 3.2 to 5.7, good gain on 4.2, and the low values of SAR. So the energy that is going towards the body, that was not on a very high scale, so it was pretty safe to be utilized for wearable applications. So the design procedure has been provided by doing multiple steps, how they are contributing towards the performance. You can see the gain and efficiency, and we did it simulated measured comparison, and we also did the circuit model, and through the circuit model simulation, how it is corresponding and agreeing to our CAD model results. You can see that we did the bending analysis into different directions as compared to a coin that should be just like a first pour of my finger. um, it is pretty easier. So we did made a polymer sheet. It is just two mixes mixed together. We let it settle down for some time, and it becomes a flexible transparent kind of like a rubber material. We cut the back radiator, and then we put it together, and here you can see the currents distribution and the co and cross poles over here. We did the bending on different bending curvatures, horizontal and vertical bending, and you can see that the radiation efficiency remains pretty much stable. Okay, we did the analysis for the body model. We put the antenna on the front side of the chest and on the back, and you can clearly see that zero point 0.8 and 1.6, 1.5 and zero point 0.3. So it gives a very low SAR values for these scenarios, and they're pretty much suitable for on-body applications, and the hotspots you can easily spot. I believe I have only like 5 to 10 minutes remain, or it's more than that, because I want to devote time towards the question answer session, and we can talk more about little bit more freely on the things. Okay, then we did another work in which we used a mixture of carbon nanotubes. Carbon nanotubes, they are very interesting materials. They are stronger than steel. The problem of rusting, that is a typical problem with most of the metals as they are exposed to the moisture or towards the water content, they started having a problem of oxidation, and the rusting is not good for their durability, and also the performance gets bad when there is a rusting on a metal, because it becomes like a blocker for the flow of the electrons, I will say. So what we did is we made PDMS slabs, and then we put carbon nanotube based material mixed with the polymer to create an other conductive polymer sheet, and then we cut it into the specific way either, or the other way is to use a 3D printed mold. So in this particular scenario, what we did is we made a mold to reflect each of the layers. So we made a mold in which that first top layer was at the bottom with the step size. Then you increment another step size for the PDMS material slab, that is gray color over here. So second step is that one, and the third step we put the ground plane on the back side, that is a full sheet of um, CNT based material, the conductive one. So once it's settled down over the time, then you just take it out, and then any extra material on the side, that was just to make sure the steps are there, to have an accuracy of the height of the layers, that can be removed. So these antennas over here, we started with a single antenna. Once the single antenna was made, the dimensions were 32 cross 35 into the height, that is 2.5 The bandwidth was pretty much wideband, 5.7 to 6.2. And then we moved forward to make a MIMO configuration. So we came up with two-port solution, um, where we have an arrangement that is orthogonal to each other to minimize, because these are the linear polarized antennas. So if linear polarization is over here, I can put another one on 90 degrees, so they don't create problems for each other. If I put on the same, then both are singing together with the same sound, and that will be a little bit problematic. So the isolation is basically in presence of the other antenna, how much impact is created. So the disturbance level, I will say the isolation is pretty low. We check the SAR values for these two antennas, and like a normal one in the MIMO configuration, and you can see that 0.17 and 0.16 for 1 gram, and for the 10 gram it is 0.04 and 0.05. So very low values of SAR when we placed it on the chest, on the front side or at the back. We did two kind of analysis for these configurations, because it's a MIMO configuration. So either you can use it for the wearable devices, or you can use it for the vehicular applications. So that is one of our recently work from this year, and that is published in scientific reports. Okay, so again, stepwise evolution of the design. We started with a simple rectangular antenna, then we started having um, stubs to be added on one and other side, and you can see that it started from a basic, and then widening the impedance bandwidth, and then finalizing it. So we did the testing of the simulated and the fabricated version, and you can see that the wideband is there. Okay, so sorry, let me make sure I'm not missing anything. Okay. Here you can see the 3D radiation pattern of the single antenna. You can see that it is pretty much on the upper hemisphere. There is a little bit of radiation going on the other side, but due to full ground plane, very less radiation is going on the back side. At different frequencies, you can see that it is fairly on the upper hemisphere, a little bit tilted towards one side. And in terms of gain, the gain is roughly around 4 dBi on average. Okay, so this is the 3D mold I was talking about. We did some stepwise structure. So we just take the CAD model, we created the different layers over here. This is just a 3D printed one. We use a material that is pretty much smooth, the resin based. If you're using the extrusion base, it will have like not a very fine quality finishing, and that can just cause a little bit of um, abnormalities in the design when you're taking it out. Other way is you can create different layers of a specific thickness. You can use glass if you don't have the 3D printed version. Just put some kind of blockers on the side with the same height. Make it a little bit bigger, and then you can just cut it onto the right size. So we did the first layer. So when we pour that mixture into that one, it will look like this. And any additional things over here, we can just scrap it by scratching or cutting it from the mold. because there is a possibility when you're putting the solution into this 3D printed structure and the grooves, it can just overflow. If your balance is not right, those are a little bit of fabrication glitches. So any additional material, you can just cut it down to make it leveled. So once this is settled down, it takes few hours. So it took us like 4 hours. We placed it under the oven, not the microwave oven. Otherwise, it will just go away. So that was roughly like 60-degree temperature for 4 hours. It settled down. So we just increased the temperature. So it gets the curing process little bit accelerated. Then once it's done, then you put another layer with the PDMS material without the CNT because it will be conductive. In step one, the step two layer is non-conductive. And once it's settled down for another 5 hours at 60 degree, we put the third layer, that is again a mixture of carbon nanotube based material with PDMS. So again, let it settle down for several hours into the oven, and then we can take it out, and then we put the connectors. Okay, there might be a question over here. We normally put things together with the help of solder. So if it is a plastic based material, how the conductive solder will do the job? Okay, so we use a conductive glue. So you just put it over there and put the conductive glue, like in the normal way where some materials or the parts can be glued together. So we dropped a small amount of conductive glue, just like a solder, and it helped us to get the connections smoothly over here. Okay, so I will show you some of the current distributions, how the current is flowing into that one. So you can see that high conduct current activities over here and here and in those areas. And we did the bending analysis again onto different curvatures, like a 30 mm cylindrical surface, 50 mm, and no bending. And you can see that it is pretty much stable in it. There will be a little bit of change, but if your bandwidth is more than the required, then your band will be here somewhere in the middle, and the edges will not be of concern. You can see that when you do analysis of the MIMO antennas, how it could be. So what you normally do in practical, that if the signal is going here, you will just terminate the other port with the 50 ohm match, so it's not contributing and not reflecting too much. So this is one of the ways how you do it. In If you want to make it as an array, what you can do is you can feed both ports together in such a way that there could be a phase difference or could not be a phase difference. If there's no phase difference and the distance between them is right, they will just either constructive or will have constructive or destructive interference. Okay. And if you create a phase difference between them, and then they will just try to steer the beam into a different direction. So these things are possible. We also evaluated different criteria. There could be ECC or the diversity gain um, as a criteria to evaluate the MIMO performance. It needs to be pretty low, and you can see it is pretty much low over here. And then the diversity gain again low as well. Okay, we evaluated the performance by putting antenna onto the body model. We placed it on the chest and the back, where it can be used for most of the applications. So you can see the gain is pretty high, 7.6, but the radiation is away from the body, not towards the body. You can see over here, the yellow colors, they are representing the low values over here, significantly low, close to like zero values. Over here, you can see on the backside again for the off-body communication, pretty good. We again evaluated um, the absorption of the electromagnetic signals in terms of SAR. SAR stands for specific absorption rate. Evaluated in two criteria: 1 gram absorption and 10 gram absorption. And you can still see that it is pretty low compared to 1.6 and 2 watt. Okay. Okay, so another thing is that we try to evaluate the performance when we put it onto um, the vehicle. You might have seen different kind of antennas on the vehicles. There could be a monopole kind of structure just sticking at the back over here, close to the back mirror. Um, that could be for different purpose. There could be AFM and FM radio antennas. There could be antennas for GPS for different applications like CB radios that are 477 megahertz in some parts and 460 to 470 megahertz range. They could be here. You can also have a shark fin kind of antennas. Most of you have noticed. If you haven't noticed it, when you are walking outside and you pass by any of the cars, try to look into the antennas that are installed over here. Um, these kind of antennas are significantly important when it comes to the cars of the modern ages. They can be used for satellite communication. They can also communicate from car to car. There could be communication for assisting the cars with the driverless um, operations. You could have sensors that are communicating here and there, and then it can be used for vehicle to vehicle communication. Okay. um, they can also be used as boosters to enhance the performance. So if you're putting an antenna that can catch the mobile signals from outside, and you can have a repeater that will just transmit it again inside the car, so you don't have to worry too much about it. Some of the applications where you don't want to go outside to get the signals, one of the simple examples could be if you're in a car and you are looking for the signals, it's a closed car. I will put a very light note that, okay, we are into a safari. A lot of animals are there, and you don't want to step outside to experience the wildlife. So you are just sitting inside the car is closed, and there are a lot of animals outside. So you might need the signal to be coming from outside inside the car, because there could be a lot of metal around and the signals are not able to come inside. So in that case, you can have some antennas over here, or you can also fit over here next to the bonnets. There could be different kind of antennas that could be installed into um, the front or the back of the car, or on the roof. Okay, so we evaluated the antennas into this kind of specific conditions where vehicle applications are there. You can see that the radiation patterns are pretty much on the upper hemisphere. They are pretty much focused into the upside. So if you are driving, you should be able to communicate into all directions easily, and also with any signals coming from the sky side. So you can see that on two different planes. So we try to get one horizontal cut and one vertical cut. You can see that it has fairly wide beam width for the communication. Okay, let me summarize the things, and then we can finalize the discussion, and we'll move with roughly like 15 to 20 minutes of um, question answer session. um, if there are any one-to-one questions, I'm still happy to answer during this time. Okay, so let me recap what we have done. We have started with the requirements for different kind of applications on the body area network. We classified the body area network into the communication side, and then based on the placement of the sensors or antennas into different categories. One is inside the implant communication to the outside over the body, that is in body communication. When the sensors are placed on the body, communicating from one point to another point on the body, that is on body communication. If you want to transmit the data from the sensors collected on the body to a access point far away from the body, that will be off body communication. If you're communicating from one of the sensors on a person to another sensor located on other person, that could be um, a body to body communication. Then we looked into antennas with rigid substrates or with semi rigid and flexible substrates. We started with a single band antennas for um, WLAN applications, Wi-Fi applications, 2.45s, 3.5 gigahertz 5G bands, and also for WLAN 5 to 6 gigahertz band, public safety area network at 4.6 gigahertz band, 4.9 gigahertz, and then the satellite communication bands that can be covered, and the latest Wi-Fi bands that can go up to 7 and 8 gigahertz band. So we have looked into single band antennas, dual band antennas, antennas with controlled radiation pattern that allows you to have a wide coverage area. We looked into antennas with CPW feed, with ground plane, full ground plane, partial ground plane. Then we looked into antennas with flexible substrate, ultra wideband antennas, and some antennas that can have a different kind of profile, but depends upon what kind of application you're using. They can have different use cases. We have evaluated antennas that are flexible onto the body, with copper tape that is easily stickable to the structure of the antenna. We also did radiating parts that is mixed of carbon nanotubes, and also um, the mixture of polymer based substrates. Carbon nanotubes, unique properties. They have very good mechanical strength. They are highly conductive. They're stronger than steel multiple times. They are very good conductors. And the problem of rusting is not there. That's one of the key things. And they're very lightweight as compared to the metals. We evaluated antennas for different applications on the body with the SAR analysis. I mentioned two kinds of SAR analysis. One is based on 1 gram criteria, and the other one is based on 10-gram criteria. Bending analysis is one of the key things in wearable applications. So bending vertical, horizontal. There is a different kind of bending. It's referred as crumpling, when you try to squeeze the antenna and there is multiple bends into the structure, that is crumpling. Um, we also evaluated those antennas for vehicle applications. MIMO configurations have been explored, and the MIMO criterias, performance criterias, have been analyzed. So with this thing, I will say that I will conclude my talk over here, and we can move towards the question answer session. So I believe we will have like roughly 15 minutes for the question answer session.
Dear participants, if you have any clarification, you can unmute and ask your queries. You can clarify your doubt. Thank you, Professor. Thank you for spending your valuable time. Thank you.
Thank you. And
Dear
it's really good to
participants,
see that we have roughly like 50 people in the session. That's pretty good.
no, sir. Now it was, and when we start, it was 50. Now it was 105.
Oh, wow. My screen just got updated now.
Yeah.
Thank you.
You can put your questions in chat.
Anyone with any questions?
Sir, yes, I have a one question.
Sure.
Which material is preferred for the bending material antenna design? You have told me about some various material, but which one is the best one, sir? For the,
Um, it depends upon the application. Some of the materials, they can sustain a high temperature, depending upon what's your application in terms of bending, in terms of indoor, outdoor, and the exposure. If you There is one of our papers, I can put into the chat which one it is. It describes a lot of materials in one of the reviews, and that could be really pretty good to go through. We listed multiple substrates as a conductive material and as a substrate, with the properties and some of the links to. to the places where you can find it. But again, it depends upon what kind of applications you have.
Sir, one thing, if I have to do in application of energy harvesting,
Yep.
in the energy harvesting, which material I have to utilize for
Okay,
the
energy harvesting, let me put it two conditions. Energy harvesting, you just need a device that is fixed somewhere. So in that case, you don't need a flexible option. It could be low cost FR4 that can be just that can have an antenna that is just placed into the device. That's it.
no,
If you
sir.
are having a mobility solution, then you
Yeah,
might need the bending into that one. So a
yes, sir.
semi-rigid will be a better choice. But if you are um, looking for a solution for a variable application, you
Yeah.
might need to include the antenna into the vest, into the jacket, into the clothing. So in that case, it could be based on PTMS, such as polymer based materials, or it could be any rubber kind of material, it could be any other material. Cotton is also a good dielectric, although it has low values, but it could also be a good option. If you want to have a very high values of dielectric constant in variable applications, that will be a little bit hard. You can also use jeans material. It has low epsilon r values. I will try to get that one and put it into the chat. That specific paper I'm referring to, it has like a good tables in which we have listed different materials with their properties and some of the use cases. Again, it depends upon your application in particular.
Thank you very much, sir. Thank you.
Welcome. Anyone else with any questions?
Sir, can we explore the postdoctoral opportunity in your university?
That's a very tough question, to be very honest.
Yeah.
Postdoctoral, if I talk about Australia in general, postdoctoral opportunities are very less, I will say, in general. And if there is like one or two positions and there are like 10 people graduating from the university, most probably they have the better chance because it will be one of the PhD student work that will be continued. Other thing is little bit challenging is the working rights. So most of the places they ask you for the working rights, and the sponsorship trend is very less, to be very honest. And same thing is applied for the industrial side. If you want to apply for any of the industrial positions, until unless the company already has explored the possibility of getting a person locally, um, and they are not successful, then they will go with international candidates. But most of the time, if you don't have the working rights, it will be very hard to get into the workforce.
Okay, sir. Thank you very much.
Professor, I have a doubt.
Sure, please go ahead.
For implantable antenna, what type of material we can use as substrate as well as conducting material?
Okay. So
Implantable antenna.
implantable antenna. So when you talk about implantable antennas, one of the key consideration will be a biocompatibility option. If if you leave any metal inside the body, it will not be a suitable choice until unless it is biocompatible. I will go with a very crude example. Let's say you cannot leave a piece of metal, let's say a brass or something like a bullet, cannot be left inside the body of a human because it will start making some kind of problems, and the muscles will get damaged, and there could be some poisoning in the body, and that can lead into more complications. So most of the time the material needs to be biocompatible. So any biocompatible dielectric that could be there. And also you need to have a metal that is biocompatible, or some biocompatible coating can be done on the device. That is another option. If you are making antenna with a normal thing but you seal it from the surroundings with the biocompatible coating, it could be there. So that is more feasible option if you do a biocompatible sealing around the device.
Okay, thank you, Professor. So that material we have to synthesize it. How we are doing it for the tablets.
Yeah, something like that, but the layer shouldn't be dissolving around, over the time it shouldn't dissolve. So it
Okay.
needs to be biocompatible material that doesn't cause any harm inside the body, and it could be there. Like for endoscopy, they now have the capsules that can be capsule antennas with all the cameras and sensors and everything. You just swallow it like a normal medication. It will go into the intestines. It will do all this the scanning. Now they have a very teeny tiny robots, and the robot can be used to do the movement inside the body, and they can go up and down, and that can do a lot of operations inside the body. Compliance is another thing that is very critical when you talk about implantable devices. Electromagnetic compatibility. Let's say you put anything inside, and you're passing by some area where there's a high frequency, strong signals, and it can disturb the implant. So that's why when you are going through the scanners, most of the time, if you have the implants or something like this, you have to let them know that I have the implant, and they will not let you go through that specific high frequency and high coverage area signals places. You're mute.
Thank you.
Anyone else with any questions?
Hello. So
Yeah.
I have a question, sir. So how can we design with variations with the temperature on the antenna or effect
Oh,
of temperature on this antenna? So actually, we are also doing this wearables and implantables. We had a query related to that. How to check it for a paper what we are submitted.
okay. Depends upon again your use case. Um, there are chambers available that can have a controlled environment. So those chambers, normally we have used those ones in RFID sensors. Let's say I have a sensor, like RFID chip. It goes onto the product. The product could be in a cold storage. It could be in a hot oven area. It could be on a normal temperature. So we change the temperature and then check the response of that thing. So similarly, you can put your implant into the solution that is equivalent of the body model. You put it inside the chamber, and once you put it inside that environment chamber where the humidity temperature could be controlled, you can check the performance over the time.
Is it possible to do it in the simulation setup?
Uh, it is possible, but not with CST or HFSS, because these are the two highly or widely used softwares for antenna design, but they have the counterparts. So the mechanical software such as Creo for from ANSYS, that could be utilized, or SolidWorks, that is the equivalent of CST but in the mechanical side. So they
With the
can do,
combinations we can.
yeah. So SolidWorks is pretty much another version of CST, but it is for mechanical simulations, where you can change the temperature. You can also do the stress analysis. You should be able to do the bending analysis. What kind of bending analysis we do in a CST or HFSS? It's you bend the structure, and after bending you will see that what is the RF performance. But if you go to SolidWorks, you bend that one and you will see the forces onto the structure and what will
Stress
be the
analysis.
breaking points. So stress
Stress
analysis, yeah, so that will be able to help you with the stress analysis and the breakup points. You can also do the temperature change in the simulation, but it has to be done in the SolidWorks,
So we
not
should do
in the
only with
CST.
the experimental analysis for this temperature variation.
If you are talking about as an antenna design engineer, yes, it's better to do it in the reality, and that will give you more realistic results, because simulations is just an approximation.
Thank you, sir.
No worries.
one, Professor, one more
Anyone?
query.
Sure, sure. Go ahead.
Sir, in your industry, which software you prefer to design the antenna?
Over the time I have used, I worked in a couple of places, and most of the places they have both softwares in the uni and in the um, industrial side. Either it's CST or HFSS, and some of the companies they have both. These are two widely electromagnetic simulators. You can also use Altair FICO. These are some other versions of the simulators. You can also write your own code. Some of the people they prefer to have their own code either in Python or MATLAB, and some people they are so much sure based on their theoretical knowledge, they will just do the calculations on the paper with the equations, and they will straight away jump into fabrication, and they will come up with the right design, and they will tune it in real time. I hope I answered this question.
Yes, yes, thank you. Because mostly we were working in HFSs or CST.
I believe these both are good enough.
Okay, thank you.
So I'm just leaving my email into the chat. If anyone wants to get in contact with me later on for any kind of questions or help, feel free to drop me a line. But just let me remind you that you are one of the attendees from this online lecture, so I can easily recall that what I have already discussed with you, and it will be just a accelerated communication. Anyone with any further questions? I will add one comment while someone try to ask a question, that the theme of this 6 days workshop was also including reconfigurable options and machine learning AI. There could be a question how we can utilize AI in this kind of work. Um, that can be utilized in a different way, but in this work it might not have very straightforward application. But if we are using um, to create antennas for 6G communication or 5G, then you need to have a beam into a particular direction, and to steer the beam or change the direction of the beam, there could be some surfaces such as metasurfaces, and the combination of those metasurfaces needs to be changed in real time, either through electronic communication or the feeding structures, um, and then that can help to steer the beam. So over the time, if you have a metasurface that has multiple options, let's say 100 unit cells, or maybe more than that one, you cannot calculate in the real time all the things. So you have a database that has evolved over the time, and the learning trends are there, and once you say that okay, I need to steer my beam from this particular direction A to a direction B, definitely over the time the AI system and machine learning system has developed the learning skills and the knowledge to came up with 100 weights on 100 elements, that these are the 100 weights. If you put that specific combination of weights, what will be the outcome of my beam? So that could be the place where AI processing can help in a real time to take quick decisions. Anyone with any questions, or we can finalize this?
Thank you, Professor.
I was just scrolling through the list and I can see people's name over here. Thank you everyone for joining and being with me.
Thank,
Thank you.
thank you, Professor, for spending your valuable time. I'll share you all the details through mail as well as
Sure.
what Professor
Great.
further days. Okay, thank you. Good
Thank you
night,
everyone.
Professor.
and enjoy your evening. Have a great
Yeah.
weekend.
Thank you, sir. Thank you.
Bye bye for now.